When you need more storage on a traditional physical server, you simply plug in a hard drive. But scaling storage in the cloud requires weaving new capacity into abstract logical layers without disrupting the entire system. An AWS Elastic Block Store, or EBS volume, starts as a completely raw, blank slate. Before your Linux operating system can even read it, this empty block must be explicitly formatted, logically mounted, and securely bound to the system architecture. There is zero margin for error here. Execute the wrong format command and you instantly wipe existing data. Make a single typo in a configuration file and your server will permanently lock up the next time it tries to reboot. The ultimate test of managing these volumes comes when you run out of space. You have to expand the capacity of a live running database on the fly without taking your application offline for even a single second. Mastering these administrative commands is essential for infrastructure stability. By controlling how data is knopped and preserved, you ensure that your storage remains persistent through updates, reboots, and scaling events. Let's start with a running Linux instance. We've just attached a brand new raw EBS volume via the AWS console, and right now it is sitting invisibly in the system's background. To find it, we use the command lsblk. This acts as our system radar, listing every block device and partition currently attached to the machine, whether the operating system is actively using them or not. Looking at this logic tree, top branch NVMe 0N1 runs the OS. Below sits our unmounted target volume NVMe 1N1. Before modifying NVMe 1N1, we verify its state with file-s. If it returns data, it's empty. If it returns XFS file system, formatting destroys active data. Running this exact verification check is mandatory. Skipping it is the most common way engineers accidentally erase critical databases during routine migrations. Now that we know the drive is empty, we have to give it a readable structure. We do this with the mkfs, or make file system, command. Typing sudo mkfs txfs with our path applies the XFS file system, structuring the raw space into an organized grid Linux can read. Next, mkdir creates an empty server directory, serving as the physical access point and logical bridge to this grid. With the directory created, we execute the mount command. This links our formatted NVMe 1N1 device directly to that new folder. We can confirm the link worked by running df-th. This command forces the operating system to reveal the drive's total size and specific file system type. The volume is now fully active and ready to store files. But right now, this connection is highly volatile. If the server loses power or restarts, the operating system will instantly forget this mount exists, and your data will disappear from the file tree. During a standard reboot sequence, Linux clears its temporary runtime memory, which includes the manual mount command we just executed. To make this configuration permanent, we must extract the exact parameters the system is currently using. We find these by reading the system's temporary tracker file, /etc/mtab, which generates a dense, complex string of mount parameters specific to our volume. These parameters dictate exactly how the drive boots. If you attempt to type this string manually into the permanent file system table, known as fstab, and you miss a single comma, the server will fail to boot entirely. The safest method is perfectly copying that entire parameter string directly from the mtab output, opening /etc/fstab in a text editor and pasting the string exactly as it appeared. When you paste that new entry in, leave every other line in the file completely alone. Modifying or deleting any existing fstab entries will break your root configurations. Saving that file completes the architecture. You have successfully upgraded this storage from a temporary runtime patch into a permanent, reboot-proof piece of your infrastructure. Eventually, your application will max out this storage capacity. When that happens, you need to add more space immediately without taking the server offline. Step 1 happens outside the server. Inside the AWS console, you select the volume and modify it, provisioning additional physical gigabyte capacity. Be absolutely certain about the size you need. AWS enforces a strict, irreversible rule for EBS. Volume sizes can only be increased. You can never decrease the size of an EBS volume once it is expanded. This comparative chart shows what happens next. LSBLK shows the top bar, our physical hardware, has successfully expanded. But DF-TH shows the operating system, bottom bar, trapped at the old limit. XFS GrowFs forces the logical file system to stretch, filling the new hardware space. Expanding this data volume is straightforward, but expanding a root OS volume requires an intermediate step. Root volumes require you to run the grow part command first to stretch the partition itself, before you can grow the file system. Maintaining true cloud agility relies on mastering this two-step sequence. You push the hardware boundary outward, then instruct the logical software boundary to expand into the new space. We run df-th one last time. The system returns the new, larger capacity, definitively confirming the operating system now recognizes every gigabyte we provisioned. We started with a raw, unusable block of digital space. By verifying it, structuring it, mounting it, and securing its configuration, we turned it into a permanent, dynamically scalable drive. This exact sequence is how you manage the entire spectrum of AWS storage. The commands remain exactly the same, whether you are provisioning high IOPS solid-state drives for intensive databases or low-cost hard drives for cold archiving. Understanding how to safely manipulate these volumes gives you total control over your server environment. You take raw storage, which used to be a rigid hardware constraint, and turn it into a fluid, highly scalable asset.